The reason that we wanted modular arithmetic here is that we started from the question about coloring knots. If we had started from the question of coloring tangles, we might have had more latitude to work with. Because we started with knots, and we knew that there were a certain number of crossings, and we were never going to have more colors than the number of crossings in that diagram. But if we start with tangles instead, let's see if we can come up with a way of assigning colors to tangles that doesn't presuppose how many colors we need. Right? So we sort of boxed ourselves in to say, let's try to do it with 3 colors. But if we don't presuppose how many colors we need, then we're also not going to presuppose a modulus on our arithmetic. And we're going to try and come up with an equation that can tell me how to turn 2 colors at a crossing into a 3rd color, right? That will let me keep going without presupposing what my modulus is. So the way that I'm going to get that is I'm going to tinker with this equation just a little bit mod 3 before we go any further with it. So what I'd like is I'm going to solve this equation for z real quick. So I'm going to say z is congruent to minus x minus y. Let's subtract it to the other side, mod 3. And then what I'm going to do is I'm going to take the coefficient of x, which right now is -1, and I'm going to replace it with a nice positive number, which is congruent to -1 mod 3. I'm going to replace it with a 2. So what I'm doing is I'm trying to come up with an equation that I can use on the integers that when I reduce it mod 3 is going to give me the same relationship, which over the integers might give me more to work with. Right? And so this is the one that I'm going to use. If I just remove the mod 3 requirement, and I turn this congruent sign into an equal sign. What this is going to do is this is going to give us a rule for coming up with a coloration for a tangle, which if we can then close up the tangle and reduce everything mod 3, then I'm going to get a 3 coloration that satisfies this equation at every crossing. But in the meantime, we have more integers to work with, infinitely many of them, and so maybe we can use that as a way to start coloring tangles. So how this works is we'll start, again, as we did in the beginning, at this part of my tangle up here in the upper corner, by labeling my first 2 strands 0 and 1. And so if x here is 0 and y is 1, then z is going to be the color of the 3rd strand at this crossing. Right? And how I get that color is I'll just take twice my x and subtract my y. So 2 times 0 minus 1. So that's going to give me another integer, -1, which I'll then label at this crossing. Okay. So already we're getting something that looks a little bit different, but let's sort of chase it through and see what happens. If at every crossing I apply that same logic. Right? So this blue strand here is -1 still, and it will remain -1. And this red strand is still 0. Now, what's this next strand after this crossing going to have to be? If the over strand is -1, this strand is 0. 2 times -1 minus 0. I think that's going to be -2 now.
Oh, yeah.
Because here I'm thinking of x as my overstrand and y as my understrand.
Oh, okay.
So there's a couple different ways to think about this rule that we're using here to assign new colors. Let's be -2. One of the ways to think about the rule that I like is the overstrand is always the average of the 2 understrands in this formulation, right? So here the overstrand was 0, and on either side was plus and minus 1. So the average of plus and minus 1 is 0. The average of 0 and -2 is -1. So that's, when I go through these diagrams, that's how I keep them straight. So the average of -1 and something is going to be -2 here, so that's got to be -3 in that case. So reach for another color. -3. And then if we keep going, the average of -2 and something is going to be -3, and so that's got to be -4 if we move on to there. So then that whole strand is -4. But then my red 0 strand is going to come down here. And now the average of 0 and something has got to be -4, so that's actually going to end up being -8 when I cross over to this side. And then the other one's got to be, yeah, I think you're right, negative 12, because an average of negative 4 and negative 12 is going to be negative 8. So let me color that one white, maybe. Negative 12. And so if we look out at the ends of this tangle, at the ends of my tangle, I have the numbers 1 and negative 3 up here at this end. And then down at the bottom, I've got 12, negative 12, sorry. And then at the lower left, I've got negative 8. And so it's worth asking, what is this coloration of the tangle? What's going to happen if I take this coloration and I just reduce everything I see mod 3? Right? Is this going to give me a valid way, if I connect up the strands in some way? Can I relate this back to a 3 coloration of the knot that I get by closing this up? For instance, if I were to try and form let's start with the denominator closure. If I form the denominator closure of this knot, of tangle rather, it's going to have to connect up those sides. But then that means that this color and that color are going to have to be the same. And so negative 3 is going to have to be the same as negative 12. 1 is going to have to be the same as negative 8. And in mod 3, that's true. Right? So if I form the denominator closure and I reduce everything mod 3, I'm going to have a 3 coloration for the knot, which we get from that closure. So that's cool. That means that the denominator closure of this is 3 colorable. And that denominator closure actually is the 6-1 knot that we had on the previous slide. So I think that my tangles were just rotated in the wrong way. So that tells me about the denominator closure knot being 3 colorable. What about the numerator closure? It's not going to work mod 3. In order to get a coherent coloration here, what modulus would we have to use? That makes, yeah, 1 is congruent to negative 3 mod 4, and so is negative 8 congruent to negative 12 mod 4. So if we reduce everything here mod 4, we're going to get a 4 coloration of that knot, or possibly link. We haven't done I haven't looked at this closely enough to know whether that's a knot or a link.
It is a link.
It's a link.
Yeah.
So it turns out to be a link, but that link then is a 4 colorable link. So this seems like it could be a fruitful avenue to explore, and it's where we're going to jump off kind of when we resume this thought process next, is that if we color a rational tangle using this scheme up here, right, that z is equal to 2x minus y at each crossing, and we start with a 0 and a 1 up at the upper left-hand corner where we begin building our canonical form of the rational tangle, and we just chase it all the way through, this gives us an algorithm that's going to let us color every single strand. Then by looking at the colors of the strands at the vertices of the tangle, first of all, how do we know that the same modulus is always going to work at the horizontal ends, right? That the 1 was congruent to negative 8 mod 3, and so was negative 3 and negative 12, right? How do we know that's always going to happen? And what, if anything, do those numbers tell us about the rational tangle? What does the colorability of the tangles tell us about the rational tangle? And what's super awesome about this is that answer actually relates back to the fraction, the tangle number for a rational tangle in a specific way. So that's how we're going to sort of dip our toe into the waters, is that we're going to first look at how tangle colorations turn back into knot colorations. And then from there, we're going to look at colorability and colorations as an algebraic object. So we've gotten a taste of it now, right, that we're doing modular arithmetic, and so it feels like there's a group somewhere lurking in the background, and that's true. But the kinds of objects that we're ultimately going to use to represent colorability are something that's more intricate than a group, something called a quandle. And the fundamental quandle, which is lurking over here in the margin, and this is one of our topics coming up here. The fundamental quandle is going to be the object which encodes all of the colorability information for a given knot. And it's the only example we're going to see this semester of a complete invariant for knots. If we can get our hands around the fundamental quandle for a knot, then we understand everything about that knot. The hard part is it's a mess to get our hands around in general, right? For some simple knots, we can do it. But the best we can hope to do, for the most part, is to see sort of shadows of the fundamental quandle, groups that are related to it, polynomials that are related to it, And those are very powerful in and of themselves to differentiate between a lot of different kinds of knots. But nothing is a complete invariant for knots on this list, other than the quantile itself. It gives us the whole picture. So that's kind of the 40,000-foot view of the rest of the semester, really.